Good morning, everyone. Welcome to fourth class of optimal design of queuing systems. So first, we'll do a short recap of what we have done. So since this is a long gap, uh, so I'll just go through in detail what we have done in the previous classes. So in the previous classes, uh, what our main objective was to uh, basically design queuing systems, right? So what do I mean when I say that if we want to design queuing systems is we want to find out parameters that the user or the um, system or the operator can choose so as to get a required output. So design means choosing a parameter by either the user or the system to get required output. Right now, uh, here all the other parameters which are not all the other parameters which we don't get to choose, if we do not get to choose, are constant, right? So they don't change. Okay, so if all the parameters that we don't choose change with respect to time, then the same problem, according to me, is a control problem. So now you have a control problem where you have parameters changing, and then you want to decide what your parameter is, then it's known as control problem. If they are not changing with respect to time, then it's known as a design problem. So what we assumed was we had an MM1 system first, then we had an arrival, and then we had departures, right? And we designed a cost function so as to either minimize the regret or cost and maximize, right? We had these two situations. Now, what does MM1Q mean? MM1Q means that the arrivals are follow Poisson distribution with parameter lambda, right? And the service also follows Poisson distribution. Or what you can say is the service times are exponentially distributed. Right. So service times, when I say service time, what I mean is that the amount of service that you give to the first packet or first customer is a random variable. And that random variable is distributed exponentially. So all the service times for all the customers that are in it at any time they're going to be served are distributed exponentially. Right. With parameter v. Okay. And here both the M's indicate the arrival distribution and the service time distribution. The one here denotes the number of servers that we have, the number of counters or number of places where customers can get into the queue and get served, right? So, okay. So first we try to design service rates or arrival rates. So do one thing. Let me. So let me first go back and see what we discussed. Okay, so yeah, I'll just do a quick recap of what we were doing. So this was a representation of what we were trying to do. So we had a service which provides service. We had a queue we had arrivals where random customers or job come in and get deposited in this queue. They service some random amount of some statistical measure you have of how much service they give. This is simple representation of the queue. So what we know are the arrival rates, the service rates, the inter-arrival distributions, which is basically the linked with the service rates, right? Yeah. Okay. So sorry. So the the the, the inter-arrival distributions denoted is a parameter which is given by lambda. Inter-service distributions also is given by mu. And yeah, the queuing discipline. So is it a first in first out? Is it a shortest job first, or is it something else, some random distribution that you pick some customer randomly out of the queue and you serve it first? So all these, so yeah. So what happens is all these play a part in uh, deciding the performance of the queue, right? So basically, there are three things how you can define all these parameters as. One is your decision variable. One is your cost function, and then what is the objective that you are trying to, right? So now your decision variables could be your arrival rates, service rates, or it could be both the arrival rates and service rates. Or you could try to find the scheduling policy that, because any scheduling policy also affects the performance of the queue, right? So yeah, are you trying to find the scheduling policy that affects the or trying to find the optimal scheduling policy? Cost functions, basically you have some function. Yeah, so some function which denotes how much waiting time each customer sees on an average, or how much, yeah, something of that sort, or how much service that you're allocating, how much resources that you're using um, to give service to the customers. So you give more service, good performance, but then you have a cost of giving more service. You need to pay more, right? So those concepts of problems. Yeah. So here, yeah. So first we look into the optimal service rate. So the arrival rate is the rate at which customers or jobs arrive to your queue. That is known. The decision variable is service rate. At what rate you need to serve service. So basically what that means is what is the random bit. So what I need to find is the random variable, the parameter of the random variable, which is distributed exponentially, that I know. I need to find the parameter mu such that some cost function. And now how do I find out this cost function? Is I look at what the performance measures that I want that needs to be either maximized or minimized. So the assumptions that I've made here are linear service rate and waiting cost, right? So first I have a service cost, yes, which is C. So what this tells us, if I choose mu, then the cost is C into mu. Then there are waiting cost H. Uh, so make a note that both the service cost that I'm working with here is linear, but this is just a model, right? It did not, in real world, this did not, mm, this this linear math need not uh, exactly map the real world, but we are trying to do a first simple case where we assume them to be linear and see how it stacks up with the real world, and if it could be complicated, could we make some changes in the assumptions, in these assumptions, right? So if a customer, yeah, so next we have waiting cost H. What that means is if a customer waits for times t, then he pays ht cost, uh, which is similar to saying that if there are I customers in a unit time, then the system pays H into I, right? So one of the assumptions that we make is a stability assumption. The stability assumption is the arrival rate is less than service rate at steady state. If the arrival rate is not less than service rate, then the waiting cost goes to infinity. So your queue blows up to infinity and there is no optimal, right? So now we define the objective function. So these are the costs. This is your decision variable. And this is your objective function. So your objective function is, so I'll denote the objective function as k, which is the unknown variable is mu, so it's a function of mu. Service cost is C into mu, and then H into L mu. So L mu, this is the expected number of person in the system in steady state, right? So now we use MM1Q property since we have made the assumption that the Q is MM1. So MM1Q, we have the following assumption: L mu is equal to lambda mu minus mu. We did the whole derivation for y expected number of people in the queue is L by mu minus lambda. We gave three methods, I think, to come up with the same. Yeah. Mm. And then, yeah, we got back to the problem here. So now this is your objective function. Here we are trying to minimize the objective functions, minimize the cost. What are the two costs? One cost is waiting cost, and another one is service cost. Right. So see mu, we have a constraint. Mu is greater than lambda in this. But we first ignore this constraint and then just go ahead and mm, differentiate this with respect to mu one time and we get this. And then we differentiate it again with respect to mu. We see that this is greater than or equal to 0, right? But this is greater than or equal to 0 if mu is greater than lambda. So in this constraint set, this function is a convex function. Okay. So to find the optimal, we get k prime mu star equal to 0. So, and we get the mu star. Right. So yeah, and we saw how this varies and what is the optimal K star. So the basic minimum cost that we pay, and then the service cost and the waiting cost, right? So this was one of the classes that we saw. And then in class 2, we did the opposite. So now we found optimal arrival rates instead of optimal service rates. Uh, yeah, and yeah, in the optimal arrival rates, the service rates are known and the arrival rate is unknown. And now here, uh, the cost functions changes because we have a reward here. So each time a customer is served, the customer is rewarded. So expected number of customers served is lambda. So lambda into R is a reward that the customer gets. Waiting cost is the same as last time, HT, which the system looks at as HI. So here system it's the cost of the system that is lambda r and the cost of the system is hi. Similarly, we have the objective function b lambda that is lambda r minus h into l lambda. This function is the same as last time. Yeah, so lambda r minus h lambda by v minus l, right? So we want to maximize this reward. We want to see that uh, people get the system gets huge reward. So you want more number of people to come. But if more number of people come, then there is a chance of high waiting costs, right? So, but now we had two more constraints. One is lambda greater than or equal to 0. We can't have negative lambda and lambda less than a, right? So basically what you're looking at is you have a mu and you have a 0 and you have this small range. Why didn't we have mu greater than 0 in the previous thing was because lambda was fixed and mu could be anything greater than lambda. That was this constraint, the second constraint. So this constraint gets absorbed into this constraint in the first case, but not in the second case. So as mu tends to lambda, what we say is p lambda tends to minus infinity, right? The closer you go to mu, it becomes minus infinity. it becomes minus n, right? Now, what happens is you could come up with a condition where, yeah, so yeah, you need to be really careful here because there are two cases. One case is where as you keep on increasing lambda, right, you see that b lambda doesn't even cross the positive. It's always negative, right? And other cases, it goes positive and then it comes back to negative, right? So now what you need to do is you need to know the constraint for which this second case happens, case two, right? This case two happens when r is less than or equal to 0. Oh, sorry, when r is less than or equal to h by mu, then lambda star is less than 0, which is not part of a constraint. If r is greater than h by mu, then the second case comes and then you have your optimal solution. I hope that is clear, right? So you need to make sure you understand how your cost function works at different cases. So you know you have an extra condition where you have r greater than h mu. You have this. If r is not greater than h mu, then your optimal solution is just zero, right? Then we saw social versus individual optimization, where social versus individual optimization means that uh, basically you decide who the decision maker is. Is the customer making the decisions or the guy who is operating the queuing system makes a decision, right? So if the customer makes decision, then it's known as individual optimal arrival rates. And if the guy who's operating the queuing system makes the decision, then it's socially optimal. So what we see socially optimal arrival rates is basically what we saw in the previous case. And individual optimal arrival rates is he just joins if he gets a reward. He doesn't join if he doesn't get a reward, right? So yeah, so then we gave an Nash equilibrium policy for the same, I think in the third class. Yeah. Okay, yeah. So first we found an upper bound on the optimal arrival rate. Upper bound, yeah, we found this lambda dash, which is 0 if r is less than or equal to and v minus hr if this. So this first case is just equal to lambda star. In the second case, this is an upper bound on it, right? And then we showed that this upper bound is basically the individual optimal arrival. The individual optimal arrival rate is the upper bound that we have defined here. And socially optimal arrival rate is just lambda star. Yeah, so socially optimal arrival is lambda star, individual optimal arrival is the upper bound that we have defined lambda star. So basically, we have the theorem that lambda, socially optimal lambda will always be less than or equal to individual optimal lambda. That makes sense because socially, if you see, you want less amount of people come. Individually, what happens is more people see that okay, I want to get the reward, I want to get the reward, so they go and join the queue. Yeah. Okay. So yeah. Next, what we were looking at was optimal arrival rate and service rate. This finishes the recap. So now we have optimally. Oh, sorry. Optimal arrival rate and service rate. So again, we will consider the N11 queue. and your arrival rate is lambda, and service rate is mu, and both are your decision variables. So both are your decision variables. Right. So now we will use the reward and cost model that combines both the features of the models that we used in the last two sections. So in the last two classes. So uh, we have our reward per entering customer, a waiting cost of H per unit time per customer, and service cost C per unit time per customer. Oh, sorry, per unit time per service, per unit time per unit of service. Now we'll write the objective function. The objective function here will be a function of both lambda and mu. And this has to be maximized because now we're writing in terms of reward, right? So we have lambda into R, the reward that each customer gets, minus H into L into mu comma lambda because it's a function of both mu and lambda, minus C into mu, 0 less than equal to lambda less than, right? And we'll replace L lambda mu by lambda by mu minus lambda. So L into lambda by so now the cost function becomes lambda into R minus H into lambda by mu minus lambda minus C into mu. Still we have the condition 0 less than equal to lambda can't be equal to or okay. So now we'll just put 0 equal to lambda comma mu and see what b0 comma 0 is. 0 minus so you are getting an indeterminate form here. So we find limit lambda comma mu tends to 0 b 0, right? So first we do a differentiation with respect to lambda. We see that r minus at 0, 0, these both go to 0, right? Now what happens with this? is lambda goes to 0, lambda by mu minus lambda. This also goes to 0 as the both goes. So this goes to 0. But we have to be clear that here there's a discontinuity at 0, 0. So if C is greater than or equal to R, right? So if C is greater than or equal to R, then lambda star equal to mu star equal to 0 is the optimal solution. Because if you give any positive value to lambda and mu, and you have to satisfy this condition unless lambda is less than or equal to mu, then you can see that so lambda is less than mu and C is greater than R, mu is greater than lambda, then you can see that V lambda mu for lambda not equal to mu, for lambda equal to mu equal to 0 is negative, right? Yeah. So, and you have the constraint that they can't be equal. So we have 0 less than or equal to lambda less than mu. Mm, We have b lambda comma mu less than 0, right? For this case. So what we'll do is we'll assume c less than r, right? And 0 comma 0 point is now excluded. And we are just in the region of lambda comma mu such that 0 less than or equal to lambda less than mu. So what we have is it contain this set contains all the pairs of lambda comma mu for which b lambda mu is greater than 0, right? B lambda mu is differentiable over this region, but not everywhere because it has a discontinuity at 0 comma, right? So then what we do is we try to find the first differentiative of we try to find the first different first derivatives, right? First derivatives we get dou by dou lambda b lambda comma mu equal to r minus h into dou by dou lambda L lambda mu. This is 0. And similarly, dou by dou mu b lambda comma mu, which is minus h into dou by dou mu L lambda comma mu. So now you need to find these terms, right? Partial derivatives with respect to L. So we know that L lambda mu is lambda by mu minus lambda. For 0 less than lambda less than mu, we have dou by dou lambda L lambda mu by mu minus lambda square. And dou by dou mu L lambda mu, we have minus lambda by mu minus lambda whole square. So now we'll substitute this and we'll get R minus H mu by mu minus lambda whole square equal to 0. This is one equation. And minus H, so plus H lambda by mu minus lambda whole square equal to 0. Well, there is a C here, sorry. So this would be minus C equal to 0. And minus C equal to 0. Okay, so basically we have R equal to H mu minus lambda square and C equal to H lambda by mu minus lambda square. So what are the unknowns here? Here the unknowns are lambda. We want to find lambda, right? So yeah. So you see we have both H. So H by mu minus lambda whole square is equal to R by mu. C is equal to this is one equation, and then we have um, so if we subtract R minus C, what do we get? We get H into mu minus lambda by mu minus lambda whole square. So square by mu minus lambda whole square. But H by mu minus lambda whole square is also R by mu and is also C by lambda. So we substitute R by mu means H R by mu, which gives us mu equal to HR by R minus C whole square, and we substitute C by lambda once, so we get R minus C whole square is equal to HC by lambda, which implies lambda equal to HC by R minus C whole square. So we have these two motion solutions for mu and m. So here you can see that so uh, lambda is less than R, right? And our assumption was C is less than. So so since C is less than R, lambda is also less than R. So therefore, this is a feasible solution. So feasible solution is mm, means that yeah, it satisfies it belongs to this set, right? So if this set is yes, then the these 2 points that we have found out belongs to the set yes. This belongs to the set yes. Okay. So under the assumption C less than R, we have identified that there is a unique interior point of the feasible region 0 less than lambda less than mu that satisfies the first order optimality conditions. So we are fairly certain that there is an optimal solution where mu and lambda both are rotation variables, and we saw that b lambda mu is both concave in lambda and concave in mu. But the thing that we have not verified is the joint concavity. So we have seen that b mu lambda is concave in mu from the previous section, and b lambda mu is concave in lambda. Right, this is from optimal service rate, and this is from optimal arrival rate. But important note, we need to make sure that it is jointly optimal. Without, okay, we need to make sure it is jointly concave. Without that, we can't be sure that it is the uh, local maximum. Okay. Yeah. So mm, B lambda comma mu is not jointly concave in lambda comma, right? That is because N lambda comma mu, which is lambda by mu minus lambda, that is not jointly concave. It's not jointly convex because the function B lambda mu has a minus L lambda. So if L lambda mu is convex, right, then this whole thing would become. So for joint convexity, what we check is we find delta, which is rho square second derivative lambda square into rho square L by into rho square minus rho square L by rho lambda domain whole square. So rho square L by rho lambda square is 2 mu by mu minus lambda whole cube. Rho square L by rho mu square is 2 lambda by mu minus lambda whole cube. Rho square L by rho lambda mu is minus lambda plus mu minus lambda whole cube. Okay, and now if you find out delta, we have 2 mu by mu minus lambda whole cube, 2 lambda by mu minus lambda whole cube, minus lambda plus mu and mu minus lambda whole cube whole square. Right, now 1 by mu minus lambda whole power 6 into 4 lambda mu minus lambda square plus 2 lambda mu plus mu square. This is equal to 1 by mu minus lambda whole power 6 minus lambda square minus 2 lambda mu plus mu square. 1 by mu minus lambda whole power 6 minus mu minus lambda whole square. This is less than 0. Right? So L lambda mu is not convex. jointly. Therefore, V lambda mu is not jointly concave. So the stationary point that we have identified here, this stationary point we identified here, necessarily does not yield the global max, right? So just to understand that, what we'll do is we'll try to put these 2 points. So what are these 2 points? Mu equal to HR by R minus C whole square and lambda equal to HC by R minus C whole square, right? We'll put these 2 points in the cost function V lambda. So the cost function was R lambda minus R lambda minus H lambda by lambda minus C. So what we get is R HC by R minus C whole square minus H, okay, HC by H into HC. So this becomes H square C H into R minus C into HR by R minus C whole square. So these both cancel out. And you have root minus H square C by H into R minus C. And you had the assumption that C is less than or equal, right? So C is less than or equal to R. So this is positive, C is positive, H is positive. And you have a negative term. So this is less than 0, which is, so the optimal point that we have found is actually worse than D 0, 0. Right? So it is therefore better to do nothing than what the point that we have found. And we know that there is a better uh, that we can do better when C is less than. And to see how much uh, better we can do, so we'll examine the problem from a slightly different perspective, right? So in one of the last class, we introduced the term traffic intensity. So traffic intensity is rho, which is equal to lambda by, right? And now we'll rewrite the B lambda comma mu, which is R lambda minus H into lambda by mu, lambda minus mu minus C mu in terms of lambda and rho. So this is R lambda minus H rho by 1 minus rho minus C into lambda by. Okay, so here we have the constraint that 0 less than or equal to lambda less than mu. Here we'll have the constraint, it is C by R, and also the constraint that C is less than R. So C by R less than rho less than mu, right? Okay. Then we'll see that B rho equal to lambda into R minus C by rho minus H rho by 1 minus. So just taking these 2 terms. So second term is a constant. The first term is positive and can be made arbitrarily large by choosing lambda sufficiently large. Thus, B lambda rho tends to infinity as lambda tends to infinity. Hence, there is no finite optimal solution to this problem. So what one can want to do is obtain arbitrarily large net benefit by selecting very large values of both lambda and mu. So uh, what does these observations uh, mean? That how much realism, how much realistic is our model actually? So that we will address in a later class. In the meantime, we'll understand actually what went wrong in a approach. So what we saw was the net benefit function in this model. Uh, it failed to be jointly concave, right? So because it was not jointly concave, and the term that is proportional to L into lambda comma mean. So we had the term h into L lambda mean. That could be written as lambda of h into W lambda. And this product term, number of customers arriving per unit time and congestion cost per time. This product term destroyed the joint complexity. So as we shall see in later classes, that these types of congestion costs, like the model that we have done for the cost functions, and the problem that we faced is non-joint convexity. So the cost function was not jointly concave or convex. It is not an anomaly, but that is a problem that we face while modeling queuing systems into an optimization. So while applying classic analysis based on the first order optimality conditions, it is not only enough to assume the values of the parameters are such that there exists a finite optimal solution in the interior of the feasible region that must satisfy the first order condition. But we must also see that uh, it is jointly concave. Okay, so uh, yeah, in the next class, we will see optimal arrival rates for two class system. Okay, so till now what we had was we had NM1Q and so till now what we had NM1Q and we had one arrivals and one departures. So, yeah, so we'll see optimal arrival rates in the next class. We'll see optimal arrival rates for a two class system. So I'll just give a brief introduction of what a two class system means. So we have an MM1 server. So new is fixed. This is known variable, right? There are two classes of arrivals count. One is with parameter lambda1 and one is with parameter lambda2. Right. So these both are your decision variables. Customers are served again with FIFO with respect to the order that they have arrived, regardless of their class. Mm. So the waiting time W lambda is a function of lambda1 plus lambda2. Right. So basically what you have is your waiting time is 1 by mu minus lambda, lambda less than mu, and infinity if lambda greater than or equal to mu. So basically what you'll have is lambda, you'll replace lambda with lambda1 plus lambda2. And the reward cost function model that we have, we'll have Ri, that is customer of ith class reward, and H1, Hi, waiting cost of ith class customer paid by the system. So we have to maximize the lambda1 comma lambda, where you have customer reward of first class, customer reward of second class, minus lambda1 H1 plus lambda2 H2 W. Expected waiting cost paid by first class and second class, right? Such that lambda 1 plus lambda 2 equal to lambda 1 greater than equal to 0, lambda 2 greater than 1. Now here, lambda is fixed. We assume that lambda is fixed in the first case. Okay, and so basically what we are doing is we have uh, people arriving at a rate lambda, but then we decide, okay, based on what the requirement is to give them two separate classes. One is lambda 1 and one is lambda 2. Right. As in the single class case, or if all rewards and costs equal to the customer, lambda 1, the the optimal arrival rate that we saw was also the socially optimal arrival rate, right? In the sense of maximize the aggregate net benefit that the customers saw. If the potential customers of class I arrive according to Poisson process with some lambda capital, then the socially optimal allocation would be that with probability AI, you choose to admit into class 1 or class 2, right? So, okay, so this is the cost function, and in the next class, we will try to solve this problem for and try to find lambda 1 and lambda 2 and lambda. So you can make either lambda fixed or you can it now it's will become a three parameter problem, lambda 1, lambda 2, and lambda. Yeah, so I'll stop.